I'm Alan Robertson, and I did found the Linux HA project, which produced the Heartbeat software, and nowadays that's called Pacemaker. And I have a number of things to give away here. There's some pins up on the front row here and some stickers. And I'm a little different from perhaps some other speakers. I like to have questions in the middle because it lets me know that you're actually alive. Some of the audiences I've been here, it's like, I wonder if I hadn't seen the move at the end, I wouldn't know. So, so if you could help me out by staying awake, because if you fall asleep, then your snoring will wake up your neighbor who's also fallen asleep. So we don't want that. So I do have these things to give away, and I'm going to give away a T-shirt to the best question. Usually, that way that works is I usually forget who asked the best question, so I'll ask you at the end to help me remember who it was that asked the best question. And the T-shirt, I'll model it for you here. You know, I've never been a model before, but I guess I can be today. So it says on the front, it says, "I see dead servers in 01 time," and on the back it has this "resistance is futile." So if you don't like bad Star Trek jokes, you're probably in the wrong place. Because one of my goals is to create as many possible bad jokes in the project as possible and incorporate them everywhere I can. So the slides are actually already up there at that location, but they'll also be available through the conference in whatever their normal way is. So let me just get started then. So what's the scope of the project is really about just discovery and monitoring. The discovery has an interesting property that it doesn't send any packets out on the network at all to discover what it discovers. And the monitoring has an interesting property in that it scales to hundreds of thousands of servers without proxies or anything else. I mean, like running from one machine. Now, that's kind of an interesting thing. And the last piece, which some of you may not be able to see, I moved it up because I noticed that you can't see the bottom part very well in the back, is that everything goes into a central graph database. So all the data we collect goes into a graph database. So a little tiny bit of history before we get started here. I originally began to think about the problems of scalability when I was working with a supercomputer. It was really a single computer, not a big cluster that had 2 million cores in it. And so I started thinking, well, how would I monitor this? It had an unusual network topology, which made it really stupid to do what's normally done. So I thought about how you would do this. Now, it had monitoring hardware built in, so I didn't have to do this. But I started saying, well, what would I do if I didn't have this monitoring hardware? And this project came out of that. So it started out as monitoring, but over time, I've added much more in the way of discovery. And today, I would say, for many people, the more interesting part is the discovery. But the two are integrated together. The monitoring and discovery are not separate. You can turn one on or turn the other one on, but they're all operating out of the same mechanism, all using the same database. And that has significant advantages, as you'll see as I go forward. And as I said, it evolved from discovering a little bit for topology, to help it be topology-aware, to discovering anything you want to discover. Just like a monitoring system can monitor anything you want to monitor. So I'm using this icon. Does anybody have the slightest idea what this is? That's a projection of an 8-dimensional cube into 2 dimensions. So I'm going to talk about 8 dimensions of the project. and as I switch from one dimension to another, I'll have a little bit of that up in the corner, just as a way of reminding myself that, oh, I've switched topics here back to the next major dimension of the project. So the 8 dimensions we're going to talk about are the problems we address by the project, the capabilities of the project to address those concerns, how we distribute work, because that's an interesting part that allows us to scale the way we do. It's probably the most interesting technical detail that there is, and the architecture that supports this, that makes this possible, I'll talk about the graph discovery schema. That is to say, how we arrange the data in the database so that we can find things. As noted here, everything on the graphs that are being passed around, everything on those graphs was discovered. Nothing was entered by hand. And in fact, I gave it no starting parameters. I just started the software, and it found the server. Everything went with that. One of the other talks talked about liking to have things be nice. I love things that are nice. So I certainly have to agree with the other speaker whose name I've forgotten who spoke in this room yesterday. I'll talk about the discovery API, because how many people here have some idea how monitoring APIs work? Pretty much everyone has an idea, yes. So I didn't figure that I need to talk about that because it's a common thing that people understand. So I will talk in more detail about how the discovery works, and you can see how it's extensible to discover whatever it is you want discovered as well. And I'll talk about the current status of the project and the project's needs. Those are the 8 dimensions. And the thing to note from my perspective, why I'm here, is so that my purpose in being here, from coming all the way from the United States over to Germany, is to get every single person in this room to get involved with the project in some way or another. You can critique it, you can write software for it, you can try it out, you can spread the word to other people. There are lots of ways to get involved. So that's why I'm here, is to encourage people to join this project. You will see that it is an amazingly cool project, and I get that reaction from people after the talk, not just before. So I think you'll find this is an unusually interesting project that is unlike anything that you've worked with before. So the first dimension is what problems we're trying to address. One way of looking at any kind of system management activity is that it's all about risk management. Because monitoring is about risk management, because you have a risk that it will take a long time to repair a problem if you don't monitor it. If you look at security, that's about risk management. Most of the things that are involved with system administration are in one way or another about risk management. The things we do that specifically address risk management is we create a detailed discovery database, and that database is a CMDB. You know, it's a graph database, but it is a CMDB that's always correct and always up to date. We discover systems that you've forgotten about. Approximately 30% of all break-ins, when they come in from the outside, not insider attacks, but outsider attacks, approximately 30% of those come from machines that people have forgotten about, that they just lost track of or were put up and no one exactly knew. So that's a big threat. This, by discovering those systems that you've forgotten about, helps you mitigate that threat, helps you take care of that threat. We also discover what licensed software you're using so that you don't have to go through and do an audit because we have the data for you. And licensed software, you know, non-open source software, most companies have some. And if you have too many copies of it, more than you have licenses, that's a legal risk and a financial risk. Since we know all the software you're running everywhere, then this helps you manage that risk. Of course, monitoring services, systems, and switches, which we do, is also part of managing the risks of having a data center and have it operate correctly. I have a habit of talking very fast. So I want to encourage you to slow me down and say, wait a minute, stop it. When I get too carried away and talk too fast. I'm trying to slow down, but it's really hard for me. So I know that not everyone, very few people here are native speakers, and that makes it harder to follow when I talk really fast. So please feel free to slow me down. And also ask questions, because that's what you're here for. Then like I said, then I know you're awake. And we don't have to, get your bodies hauled off because I thought you were dead. And the last thing is we find services which are not monitoring. Because we monitor things and we discover things, it's easy enough to compare the list of things that we have that should be monitored to the things we have which in fact are monitored, to say, oh, we've neglected to monitor these things. So it closes the loop from a quality perspective. So another dimension of this is to say exactly what risk we manage against intrusions, licensed software, audits, outages and system management. One of the things that I haven't mentioned is part of the process of managing systems is to make a decision on how you want to make a change in the future, how you want to do a migration, based on knowledge of how it is now. If that knowledge is incorrect because your documentation is incorrect, then you will make some decisions which you may have to then do some quick recovery for. And sometimes people call those in the United States career-limiting decisions. We don't like career-limiting decisions. I don't think any of you do either. So we're trying to give you information to help you make more informed. Was that a question or just waving your arm in the back? Just, okay. I was hoping. So, but it's okay to stretch too. So trying to provide you accurate and correct information to help you make decisions and understand how this stuff that you have works. How many people here think that they understand every system that they have under their control? Okay, me neither. So this is a process to help you provide you information which will help you better understand that. And from a just from an operational perspective, documentation is usually incomplete and incorrect. Dependencies are often unknown. Like, what would happen if I shut this machine down? How would that ripple through the network into other systems? If you want to check to see if you're following best practices, you have to know what you're doing. So because we gather all the data and data that you might want to add into the database, you can write scripts which go through the database instead of doing an SSH to every machine to collect the data, because the data is always collected and always correct. Barring bugs, of course, but I don't care for bugs either, but they happen. And as I said, from an ITIL perspective, this is an accurate, up-to-date CMDB. And one of the interesting things is our discovery runs all the time, so it's up to date within a few minutes or a few hours in some cases. And it is very low profile. You'll see that as we go on. So it has very minimal impact on the network and very minimal impact on the central system. So I would switch from talking about what capabilities we try and what problems we try and solve to what features we use to solve those problems. So I'm switching from this dimension to that dimension. Now, once I get past the third dimension, I don't know what I'll do. But I'll probably wave my arms in some incoherent way, but like that. So as I said, we do, so the features we have, and there's a list of 11 of them here, 5 on this page and 6 on the next, which talk about what we do to provide these. The discovery is continuous. It runs all the time, just like your monitoring runs all the time, right? It has 0 network footprint for discovery. That is to say, all the things on that chart, all were discovered without sending any packets off the machines to discover anything. So you don't have to get permission from your network people to map their network. You don't have to get permission from the security people because you're not sending pings or doing port scanning. You can just do this. How many people think it might be difficult to get the agreement of your networking and security people to do this? Exactly. This is a common problem. That's why I designed it the way we did, was to avoid, it's best to not have to ask permission. So we do create this centralized graph database of everything. We know everything that changes, so there's nothing that changes, at least nothing that we're discovering, which we won't know about. And we also discover dependency information. So we know, for example, that this machine is a client of the service on this machine. That's not as reliable as the discovery of services, but we do in fact do it. Going on further, discovery and monitoring are tightly integrated. So the way most systems work, monitoring systems, is you do the discovery by hand, and then after you've discovered everything, you tell the monitoring system, right? There are exceptions to that, but because we have this generalized discovery and it's integrated with the monitoring software, it's easy to see how the monitoring software can be informed on what it ought to be monitoring. And it can tell you, by the way, how do you want to monitor this? How do you want to monitor that? Because it knows. It's naturally scalable without any special provisions to more than 100,000 servers. I actually, early on, in an early version, it didn't have a disk database at the time, but I did a 300,000 system test, so, 300,000 simulated systems. You'll see why this might sound a little outrageous, but one of the interesting things, too, as we go on and implement the planned architecture, which I'll talk about, we can also tell switch failures from server failures. Instead of saying, oh my God, 48 servers went down. Oh, a switch went down. Which somebody was talking earlier about wanting to limit the number of pages you get from one of the talks. Well, if we in fact diagnose the problem better, we can give you better alerts. So it has very minimal network load. You'll see that much less than anything you're accustomed to. And it has multi-tenant support. We're building multi-tenant support into it. That's a recent architectural change that isn't fully carried out. But the intent is to have it support multi-tenant environments, including segregating the people from getting at only their own, keeping them to get at only their own information. How many people think this sounds unreasonable? No, somebody else has to be. That means one guy is paying attention. No one else is paying attention. So it doesn't sound reasonable, really. Discovery, scalability without a lot of complexity. Discovery without setting packets? That doesn't sound reasonable. Well, hang on, and at least one guy will figure out why it is that it might sound unreasonable. It isn't quite as unreasonable as it first sounds. The next dimension I want to cover is how we distribute the work, and there are two sort of philosophical underpinnings or principles that we follow. The first is that we distribute the monitoring and discovery completely. It is 100% distributed. There is no central server doing discovery or monitoring. The second is that we have a reliable form of no news is good news. People know what no news is good news is. Is that translating okay? Yeah, okay. So, but it's reliable. See, that's the trick. Having no news is good news is easy. Having it be reliable, that's the interesting part. So as a result of those, the consequence is that the central system only has to respond to things that change. If a system was down and it came up, if a system was up and it went down, same for services, same for discovery, if a new server shows up, if a new IP address shows up, those discovery processes only have to report changes. They don't have to report anything other than that. That's the consequence of those principles. Now let's go on and see whether we can do more than that. So, sorry, was there a question? My mistake. So I'm going to explain how the scalability works so that your grandmother would understand. So my analogy goes like this. On Wednesday nights in my church, we have a meal together, and we all stand around in a circle, hold hands, and bow our heads, and shut our eyes, and pray. Now, while we have our eyes all shut, what if Aunt Sally passes out? What if she faints? Who's going to notice? This is not a rhetorical question. You have to answer it. Answer. The two people next to her. Excellent. Now, I'll ask you another question. How many hands do you have to, if you have 10 people in this circle, how many hands do you have to participate in this monitoring arrangement? And if I have 1,000 people in the circle, how many hands do you have to participate? Very good. So, did your work go up to monitor to create an environment where 1,000 people were monitored versus 10? Not at all. 01. That's what 01 means for those of you who aren't computer science geeks. That means the work doesn't go up. It just makes the shirt really cool, though. But so far, no one is going to win a shirt because you have to actually ask them questions. Answering them doesn't count. So that's how we work, is we establish a neighbor arrangement where neighbors monitor their neighbors, not from an up perspective. You know, that's a server monitoring arrangement, just for servers, not for services. We'll talk more about that as we go on. Anybody here think that they couldn't explain that to their grandmother? It's very simple. So when you look at that in computer science terms and you draw graphs, because that's much cooler, right? You know. And I have to get out my lightsaber here. Oh, that's a different one, isn't it? Yes. So then what happens here is machine A sends heartbeats to F and B. F sends heartbeats from A to A and E, and so on. So that every machine is talking to only two machines and sending heartbeats at some modest rate. I mean, you know, it could actually be a pretty high rate because all they're doing is talking to two machines. You know, once a second wouldn't be a problem because if a machine can't handle, that's 4 packets a second, 2 in and 2 out every second, then it has a problem. And it isn't caused by this software either. So this is how it's currently implemented right now. So if you have now, this is t-shirt mathematics. So the real mathematics are that there are a piece of this work which is not O1, which goes up as the number of servers goes up. That piece of work is the work for alerting somebody, lighting the big red light. Yes, question, good, my first question.
Do you currently have like a problem? You set up no packets?
I said for discovery,
Okay.
This is not discovery, this is monitoring. But it's a very small number of packets, and they're sent unicast for every machine to two other machines, and I'll talk about a way where this 95% of it stays within a switch in just a minute. But you're absolutely right. You're pointing out, I wasn't as clear as I could have been. What I meant to say, and sometimes it's language translation, but discovery doesn't send any packets. Monitoring does send packets, but only monitoring of servers, not of services. Okay? So I don't have to send packets to ask about the web server or whatever. We'll get to that. Does this seem clear enough? Yes, another question.
How do you monitor switches?
I'll show you that in a second too. Thank you for asking. So, this is the next implementation. This is what I'd planned from the beginning, but haven't gotten this far yet. So now, instead of one ring, we have many rings. The difference is, now this ring is all the machines in one switch. So that means they're heartbeating to neighbors on the same switch. So that all the packets stay within a switch. So this is your cheapest bandwidth and your most reliable bandwidth. Yeah? Anybody argue with that? Your cheapest and most reliable bandwidth. In other words, this switch would be seeing, if you did it once a second, it would be seeing about 96 packets per second. Because every machine would be sending to two neighbors. So, which is, and they're small packets, on the order of 500 bytes or something like that, I think. But of course, if this switch goes bad, what happens? You hear nothing. There's an old science fiction story called I Have No Mouth and I Must Scream. They're all trying to complain that they can't talk to their neighbors, but they can't because the switch has gone down. And they want to report it centrally, but they can't because the switch has gone down. So instead, so to deal with that, we add a second kind of ring that connects one machine on each switch in a ring. So now, I apologize that this is low down here, but trust me that there's a ring that, I'll draw it up here. Imagine a ring that connected these three machines together, for those of you in the back that can't see the ring at the bottom. So if you had such a ring, like the one down here that's actually drawn on here, then an interesting thing happens. Now, if I apologize to the people in the back, but it's easier for me to point at the ring that's actually on the screen instead of the one that's I told you to imagine. But if this server goes down, it's on 2 rings and has 4 neighbors. How many reports will you hear that it's gone down? 4. It has 4 neighbors, 2 on this ring and 2 on this ring. I said if the server goes down, the server goes down. The answer is 4. Now, if the switch goes down, how many people report it? Exactly. So if you see a report of death of a server that's one of these that's on multiple rings, now and you're not getting reports from all of its neighbors, now you know something very strange has gone on. And in this particular case, it's pretty easy to deduce that the switch has gone down. So somebody asked earlier how we monitor switches. This is how we monitor switches. At least from the perspective, it doesn't tell you everything about the switch, but it does tell you whether it's operational, a very important perspective of a very important aspect of the switch. Now, for example, there are lots of things you can do to cause strange behaviors. There are all kinds of failures. You know, for example, that this port can't talk to that port. The truth is, no monitoring system catches all of those, and I don't either. But it has this advantage that by the time you add up all this, it turns out to be 95% of your traffic stays within switches. So if, now the top ring at the top that the people in the back actually can see connects one machine on each subnet. So if you have some piece of hardware that's unique to the subnet, perhaps a repeater or something else, then you can also detect that as well. So if the entire subnet goes out for some reason, you can see that as well. So that no matter what happens, you will eventually see something. Yes?
Quite sure. What if the servers have a bonding interface to virtual chassis switch, and one of these virtual chassis switches goes down, the server has to function to the other side?
So that you can actually see that though by monitoring things in the server. You can see that one of the interfaces is up and the other one is not. So that's a different. There's a different way to catch that problem. So it isn't perfect, but it does a really good job of telling you when the switch is crashed, right? And it does it for free. Always like for free. Now, there's always complexity in this in terms of timing and saying, well, how long do I wait to decide if I'm not going to get a report for failure? You know, and there are ways to calculate that, but it does complicate the logic some, just to be fair. So does this seem clear enough? Understand why I like this approach? This is not yet implemented, but you can see it's an extension of what we talked about before. And so if each subnet here is in a separate site, how much traffic do I have to have between sites to monitor the other sites? Very, very little. Just these heartbeat packets that go across subnets. That's it. So it also has an advantage. The total traffic on your network for this, outside of the switch, is very low, extremely low. And if this is WAN bandwidth, you're really happy to not be spending it doing monitoring. Make sense? Somebody in the back nodded. That's really good. I'm glad you guys back there. The other day when I was here, I saw people mostly half asleep in the back, so I'm glad you're awake. Appreciate that. Now, a zero network footprint for discovery. For discovery. I answered that before, but I didn't make it clear. So let me say it again. The zero network footprint is not for monitoring. And this network footprint, not for monitoring servers. It is still true for monitoring services, and it is still true for discovery. The key thing is when I talk about zero network footprint is that what I'm not doing is pinging and port scanning that will get you in trouble with your security people. How many people want to have the security people come and ask you awkward questions about why you're port scanning your network? Anybody want to do that? You want to have that happen? Yeah, well, okay. I do need agents. Yeah. Agent. So let me just tell you. So the answer is I have agents because you can't do this without agents, and without agents you can't scale. If you don't have someone to help you with the work, then all the work still has to be done.
But when you discover deeper in the system, so you need rights for the application.
So but you do have to have permissions to run commands on the machines, which normal system administrators do. You do need permissions on the machine, but what you don't need is network permissions. And you don't have to worry about your network security people coming and asking you awkward questions. I've known people who got marched out the door for doing this kind of thing, innocently, right? But here, because there is we'll talk about the discovery some more, but the zero network footprint was primarily about discovery. This is very small network footprint, but you have to do something to see that the server is still up. You have to know if the server's still up. And dead servers can't tell you, oh, by the way, I died. So somebody else has to tell you. Yes?
I'm wondering how you will detect problems when there are different servers and different VLANs on one switch, or how you
So
virtual environments.
I think for so I'm not sure which. There are different kinds of uses of the word virtual. Do you mean virtual hosts like VMware? So let's say that there's another perspective here. If I can't discover the switch topology, which I can't usually in the VLAN case, then everyone winds up basically on this subnet ring, because you do know what subnet they're on. Then instead of having these rings here, everyone winds up on the green ring. And you don't get all the advantages, but it still works. Okay, does that make sense? You don't get all, thank you, so far I think that's the best question. And if you don't want a shirt, you don't look like a t-shirt guy, but but you're welcome to the t-shirt anyway, or you can choose the second person to get it instead if you prefer. So this is the basic idea. The basic idea of the ring, it works very well. You have neighbors. We went this direction, or at least we plan on going this direction, because it makes things even better, even nicer, right? Even nicer. So the next dimension, I don't know how to draw the fourth dimension, as I said, is how the architecture works. And in particular, there are 3 architectural components we'll cover. The first one is the collective management authority, because after all, if you're going to, we call the agents nanoprobes. For those of you who don't remember Star Trek, that's what the Borg would inject people with to assimilate them. So we inject your machines with nanoprobes to assimilate them and have them join the collective, which of course is managed by the collective management authority. And we store things in Neo4j, as I mentioned before. So these are the I'm just checking the time. These are the things these are the architectural elements that support making these things happen that we talked about before. So the CMA, by the way, the slides that I pointed to that are on the web are in a slightly different order here because I was having trouble saving things and I lost some changes, so I put them back here. They manage nanoprobes. The nanoprobes are the agents. So one answer to the question of how I discover things without sending packets on the network is I cheat. I cheat because I have agents. But the agents give me tremendous value. I get both discovery and monitoring out of them, and also this scalability. So I get 3 things out of them really that are I think all very interesting. So the CMA configures and directs nanoprobes. It hears alerts and discoveries from whenever a nanoprobe on a machine discovers something, it sends it back to the CMA, which then updates the database. And then, of course, it also updates the rings. It is the one in charge of creating these rings of servers. I don't trust that to the nanoprobes because first of all, if the nanoprobes are on every machine, you want them as stupid as you can make them, because stupid software works. And also, there's a security aspect of trusting machines, a large number of machines with responsibility for maintaining your monitoring network. I want to extend them enough trust to get the scalability, but not so much trust that I get any trust that I don't have to. I don't want to extend to them for reasons of security. Does that make sense? So it also has the responsibility to update the database, and in turn to issue alerts. So what the nanoprobes do, and they're in C, the previous part was in Python, I think I mentioned that. But they announce themselves to the CMA. They wake up and they say, "Hello, CMA, here I am." And the CMA then sends them back some information. And for many people, you don't actually have to tell the nanoprobes where the CMA is. They'll find it. If you have multicast that works for one packet. I mean, it doesn't have to. We use that to discover the CMA and nothing else. Everything is a unicast except that. Now, if multicast doesn't work at your site, you can tell it where it is. You can give it the DNS name or the IP address of this CMA. But that's very nice because the stuff on that graph, I literally configured nothing. I didn't tell the nanoprobes where the CMA was because multicast works at my house, and I have really cheap hardware. So it does really 2 things. They announce themselves to the CMA, and they do whatever the CMA says. If the CMA tells them nothing to do, They do nothing. So they have no policy in them. They have no configuration except with the possible exception of where the CMA is and what port it's on. So that's the only exception to configuration for nanoprobes is whatever information they might need to find the CMA if multicast doesn't work in your environment. We went to IANA, the Internet Naming Authority, and got a dedicated multicast address for this project. Reserved multicast address. So the kinds of things the CMA tells it was, here is your configuration information, general configuration like addresses, ports, stuff like that. And it gives directives to send and expect heartbeats, no surprise. And that is not zero network footprint, but that's not the discovery. Perform discovery actions, like I want you to perform a discovery of this kind of discovery every 10 seconds from now on. And it will then perform that discovery and only send the results upstream when something changes. The Nanoprobe does that. And it performs monitoring actions with a similar kind of thing. Yes?
How do you handle remote sites, the CMA at each site?
So that's, so the question is, how do I, thank you for, someone said I should repeat the question. The question is, how do I handle remote sites? That kind of depends on your network topology. But if you're able to if you can convince your people to allow my packets to, packets to go through, then you can do it with one CMA. There are questions about what you need and all that kind of stuff that answer that more fully, but technically speaking, you can have one CMA for multiple sites. But the practical questions are different, right? Today, the CMAs believe that they're in charge of the entire universe. They don't believe in other CMAs. But with the scalability the way it is, and the fact that at least in the future we'll be able to have this traffic be very minimal between sites, the plan is that hopefully that won't become an issue. Now, in practice, it may become an issue for lots of different reasons, right? I don't plan on solving that really soon. If you want to join the project, remember I'm here to get people to join the project and solve that problem. That would be delightful. Yes, another question.
If you are in Intruder and get the CMA to your network, so the Nanoprobe also reporting to that CMA then?
Yes. So, well, actually, though, the code today doesn't have cryptographically secure signatures, but that's the plan. But it is worth noting something very closely related to what you said is the CMA is not the keys to the kingdom. However, it is a buried treasure map telling you where all the treasure is buried and how to get it out. It tells you everything. It tells you what versions of software, what ports are listening on, all that stuff that the attacker would love to know. So it's very important, and I take this very seriously. In fact, I'm starting a committee to examine our security policies to make sure that we're handling this correctly. For example, I have my son-in-law is an SE Linux developer, so he has volunteered to help us set up SE Linux policies that will minimize the chances of that happening. But it is important, very, very important. See, remember, I'm trying to create value. What if I succeed? Oh my goodness, then there's a lot of value there. Then that value has to be protected. Does that make sense? So, yeah, I understand that problem. It's not quite what you asked about, but the problem you're talking about is much simpler to solve. So they also currently don't have any persistent state across reboots. The people in the back can't see that, I know. But basically, I try not to store anything on disk. That changes. That might change in the future, but that's the current plan. So that's how now you understand how we monitor servers. Now, in terms of monitoring services, our current plan is to use an architecture based on the Pacemaker or Linux HA or Heartbeat, however you want to call it, infrastructure where we had something there called the local resource manager that does monitoring, and it's designed to monitor locally. So it's a well-proven architecture. It's been in use since 2005 or so. It does do no news is good news. And we give it it's already prepared to, we give it a task to do, and it does it repeatedly. And it is trusted to keep doing it. Pardon. Until it's told to stop. Since that's the same daemon that's sending heartbeats, if that daemon dies, the other machines will report it as dead. So you won't fail to notice that something has happened. You might misdiagnose it, but you won't fail to notice it. That make sense? So it implements the Open Cluster Framework standard, among others. Each system then monitors its own services. So, for example, if I have a web server on my machine, I issue a wget or an HTTP GET to my address periodically, look and see if the results match some regular expression, and that I get a 200 result from the web server. If I'm a database server, I'll issue a query, a simple query that happens quickly, perhaps counting what we currently do is count the number of users in the users table. But it has to actually go through all the paths of the database. It has to take the query and parse it. It has to optimize it. It has to then execute the query, get the results, and then package them up and give them back. And so that's the normal query path. So if the database system itself is hung, the chances are not very good that will succeed. So that's the kind of things we do for monitoring services. But again, once we give it a job to go monitor something, we might not hear back for it for a year or 2 years, right? As long as people do have servers that stay up for years, right? And until something changes, we won't hear anything again. It will keep sending heartbeats to its neighbors to say, I'm still alive, yes, I'm still operating. But that's all that happens. And it doesn't come to the central machine, it's distributed to its neighbors. So one of the things also at the bottom that you can't read in the back, this API is also capable of starting, stopping, and migrating services. So I'm not currently planning on doing that, but it clearly has the capability of saying, oh, that service has died, let's restart it. Because the API I'm using supports that. And it also has the ability to say, oh, if that's a virtual machine, let's migrate it somewhere else. That's also built into the API. So if you wonder if I'm going to try and take over the universe, we are the Borg, right? So the summary of pros and cons. This is kind of what we've gone through here. And there are cons, besides the ones that have been mentioned. It is simple and scalable. The work is distributed uniformly. We don't have a single point of failure. Now, the CMA is potentially a single point of failure. There are lots of solutions to that. I like, Pacemaker or Heartbeat to solve that problem. There are other packages if you don't like that one, Zookeeper, whatever. It will be capable of distinguishing switch versus host failure. And when we implement this stuff, it is easy on the LAN and WAN, very easy. And it is, we've put into it a multi-tenant approach. That isn't fully implemented, but we're trying. Lots of stuff's not fully implemented. The disadvantage is it has active agents. If you don't like active agents, you're going to not like this. Sorry. We get a lot of value out of those agents, though. We get a lot of value. Yes. So ideally, I'd want them on every system. Ideally, because currently all the discovery happens through the agent looking on the machine and, for example, doing a netstat to see what services you're offering. Yes, but I'll discover that but I'll discover IP addresses. I discover all IP addresses. If I have one machine on every subnet, then I will discover every IP address. Because I list, this code isn't written, but this one I know really how to write. It's just, if I could stop traveling. Listen to ARP broadcasts, right? Listen to ARP broadcasts. They're intended for you. They arrive at your machine. Your operating system throws away most of them. Right? Yes? IPv6, you can't discover machines this way if you're IPv6 only. It supports IPv6. In fact, the code from the ground up treats every IP address as an IPv6 address. However, ARP broadcasts obviously don't work in IPv6. I don't yet have a mechanism to discover machines in IPv6, but fortunately, probably neither can your attackers.
That's actually also a point scanning a /24 in IPv4. That's doable.
I don't do that. I don't scan any. I don't port scan anything.
Scanning a /64 in IPv6
But I don't do that, so that's not a problem to me. It is a problem to the attacker, not to me. So let me repeat the question, because I apologize for not repeating the question. So the question was mentioning that scanning a port range in IPv6 with 64 bits is virtually impossible because it's, I don't know what the number is, a long number of IP addresses in a /64, and scanning a /24 is reasonable, but it doesn't matter to me because I never do that. It does matter to the attacker. So although I don't yet have a method of discovering IPv6 addresses, I do have a way of discovering IPv4. So if every machine has an IPv4 address, I will see it. I won't necessarily know what it is, because I will see it because it will eventually send an ARP broadcast. Does that making sense to people? Or is this okay? I can't tell if that's making sense or not. Oh well. So anyway, the disadvantage. If you need clarification on something, please let me know. There's a language barrier here that I don't know how to overcome. I'm just doing the best I can. But the other thing is a potential slowness at power on. What makes this system, the weak point of this system, is not how many machines you're monitoring, but the rate at which things are changing. Does anybody see that that's reasonable? That makes sense? It's because it only has to respond to changes, then obviously the weak point is changes happening very fast. Does that make sense? So if you power on a data center of 100,000 machines and they all come on in 5 minutes, yeah, I'm not going to get this database updated in 5 minutes, boys. I'll just tell you, it's not happening, and ladies. It's not happening. So what that means is your monitoring would lag behind the startup time for a while, depending on how many servers you have and all this stuff. By the way, I have given this talk on the Facebook campus to their staff. And I had to stop them from deploying it because it isn't quite ready. We're hoping by the end of the year or first quarter to have it really ready to deploy in a test fashion. I mean, you can put it up today, but it's more of a toy as a proof of concept. But they are very interested at their scale. They looked at this and they said, this is reasonable. So like everyone else, you see that they saw the disadvantages. We had a long discussion. It went on 2 hours answering all their questions. But it is, they have a lot of computers. Not as many as Google, but an awful lot. So that's the disadvantages. So the next component in this dimension is the graph database. So does anybody here how many people here have dealt with graph databases or know what they are, either one? Small number of people, which is kind of what I expect. So a graph database has two kinds of things in it only. It has nodes, and it has relationships between nodes. So if you want to think of those as pointers, you can think of them as pointers, but they're not really pointers. But they're relationships between nodes. So one of the things that I like about it is if I asked anybody in this room, let's say we get a whiteboard up here, to come describe something about your systems that you manage, and I gave you a marker, you would start drawing squares and circles and arrows. That's a graph. What that means is the model you put on the wall is very closely related to the model that's in the database. The model that you see on that graph passing around is a lot like what you would draw yourself. So it creates, so I like the idea that in my experience, when software's mental model of the universe matches mine, I am much happier. And I don't spend much of my time with my fingers stuck in the gears wondering why I'm missing skin on the end of my fingers because I messed it up. Because of my misunderstanding. Has anyone here done that? Misunderstood a piece of software and made it worse? I know you guys wouldn't do that. I have that problem at least. So one of the interesting things here in terms of not well-known aspect, if I have a relational database, the relational database gets slower and slower and slower as I grow the tables. So, but with a graph database, the only thing that gets slower is the only thing that determines the speed of a graph database retrieval is the size of the subgraph, the size of how many nodes that you have to traverse. That's all. So if you are, so when you're processing a graph query, if you have a small number of nodes that work together and you're doing a query about it, the fact that it's in a database of 10 million nodes makes no difference. Makes no difference at all. Because you're not going back to an index to search it out. It's the index that gets slower, not the retrieval from disk. Disk, people have mirroring technologies and so on that keep the disk running pretty well. So, so the speed of graph traversal depends on the size of the subgraph. Root cause queries and lots of other queries are, in fact, the questions you want to ask, like, what all goes down if I shut this machine down? That's a graph question. That's a graph question, right? Follow the graph to all the things that depend upon it, follow the things that all depend on it, and follow the things to all the things that depend on it, and that's the answer to the question. That's a graph traversal question. And relational databases are notoriously bad at that. That's something they're very weak at in terms of performance. You can do it, but you'll wish you hadn't. When you talk about visualization, since it already maintains the data in a format consistent with how you think of it, it makes sense that the visualization will be a natural thing. I have someone who is just beginning the work on doing some visualization for the graph database. One of the things, the two things at the bottom you probably can't see in the back, so I'll read them aloud. I don't normally like to read but it says schemaless design is good for constantly changing heterogeneous, meaning all different environments. How many people in the room here have all your servers running the same hardware with the same OS and the same version of patches? Anybody in the room? Oh, I'm disappointed. How many people here have all their switches, the same models, the same brands, from the same vendors, with the same patch levels? Nobody. So because of that, the world keeps changing. How many of you don't put changes into any of those things over a period of a year? Gosh. So if you have a relational database with a fixed schema, every time you add a new feature, you have to add new fields to the database, which means you have to then reorganize the whole database. With a schemaless environment, adding new fields to the database is just adding new fields to the nodes that have that information. Those that are like on older releases that don't have that, provide that information, they're not there, and it's just fine. So the idea, this isn't specific to graph databases. It's specific to most of the NoSQL databases. But the idea of not having it be having a fixed schema, helps. So the graph model then becomes the graph model is also the object model in terms of making your system work. Okay, I have 3 more dimensions to go in 6 minutes. I apologize for being quite so slow. I tried to slow down. It looks like I succeeded. Now I'll talk about, go on to the next dimension, the next major thing I want to talk about, which is how we do discovery. Discovery works a lot like monitoring works. You write a script in whatever language, it spits out JSON. And it should spit out the same JSON unless something has changed. Don't be changing it randomly. And if it spits out the same JSON, we don't send it upstream. But if it spits out different JSON, we send it upstream to the CMA. And I'm going to give you 3 discovery snippets here to look at from OS and service and client stuff. And I'm going to be quick on the latter 2 because I'm running out of time. So I just told you this, right? So sometimes we have plugins in the main system as well to process the data that goes upstream if you want to make new nodes and relationships as a result of the discovery. Most of the time, many times you don't have to do that. Here's an example output for the discovery of what OS version you're running on a Linux machine, on this machine actually, ran it last night. Node name is LNR 1225B, OS is GNU Linux, and so on and so on. It also has, this isn't all from Uname, this is all some of it is like distributor ID is Ubuntu. Ubuntu 13.04, codename raring. I always get confused on the Ubuntu code names. Everybody refers to them, you have to know the code name, but it's like, what do I have? I don't know, it won't tell me, but my discovery tells me. So I love that because it's like I have trouble remembering all this stuff, matching up the alphabet. It's hard. I don't have enough fingers. You need in English you need 26, more in German, I think. So, and this is what it looks like for SSHD. I'm going to have to be quick on this too. But basically, the executable is SSHD. The command line is SSHD with the -D flag. So this is information, a lot of information about the command itself, and that it's listening on port 0.0.0.0. That's the any address on port 22. So this spits out saying, oh, by the way, SSHD is listening on this port and that address, which is the any address, right? And correspondingly, we also discovered that I have an SSH running. This is an SSH, not an SSHD, which is running to server user ID LNR, group ID LNR, same kind of information, except it goes to a concrete address rather than any. And I'm going to show you what that looks like in particular. I'm going to show you 2 schema subgraphs here. This is what I really want to hit. Have about 3 minutes. So this is the result of, this is on that graph that you passed around, but you'd never find it in there. So SSH is connected to this port, 10.10.5. This is the information we got from the discovery. It makes nodes in the graph that says that I'm connected to the 10.10.10.5 port 22, and the SSHD is also listening on that port. So, oh look, we have a dependency. This process depends upon that process. So now I can see that this thing has a dependency upon that just by discovering the clients and the servers. I got really excited when I had this happen. I said, oh, this stuff works. So another thing it's on, as I said, on the graph that I passed around. This is also on there as well, but this is a switch which has 2, and this is a server which has a NIC, ETH0, which has a wired to relationship with this NIC. This NIC is called G3, or switch port 3. That says this guy here, ETH0 on my laptop, was plugged into a port which was G3, which was labeled in the switch as kitchen, north wall, white jack. Now, I had to tell the switch that, but I didn't have to tell my discovery code that. So this could be wrong, but this is not. I know what port it's plugged into. Where the jack comes upstairs, human beings can mislabel that, but this is correct. Same thing here. For this machine, its ETH0 is connected to port 21 of that same switch. And this is all discovered without sending any packets out. Yes? CDP, or LLDP. No, I didn't ask. This is discovered automatically. CDP, the Cisco Discovery Protocol, or the IEEE version called the Link Level Discovery Protocol. Your switch is probably sending you a packet once a minute that tells you this information. You're just ignoring it. Another example is my mother used to say, it's amazing what you can learn just by listening. So we try and listen. She did get some things right, So our current status is we had a first release out in April. We're trying to have the Nanoprobe code works quite well. We have several discovery methods written and so on. It's licensed under the GPL. We will eventually offer commercial options as well. The CMA restructuring to do for a variety of reasons, because the first code sucked. That's the short answer, is mostly done. If I go home and stay home for a while, I'll finish it up. And the 8th dimension is get involved. That's why I'm here. How many people think this is different from anything you've seen before? Yeah. How many people think it's interesting as well? Yes. So all of you are candidates to become participants in this project in one way or another, because this is way cool. It is very different technology. It has significant advantages. And what we're trying to do is build the team up of people that are working on this. So it isn't just me and a couple other people. I have like 4 people on the project. One who works on it pretty hard, and then me, and a couple other people who help when the things are needed. But we want more people. That's how open source works. And that's what I'm here for. That's why I'm here. And the last slide, We need testers, continuous integration, designers, developers, porters, early adopters. It says here at the top. Many of you could be early adopters, people to come and critique us until it's broken, right? Fix that crap, man. That sucks. Promoters, publicists, packagers, all kinds of things. If there's a skill you have, we probably need it. Artist, anything, right? So just remember, resistance is futile. And I have a hashtag, Assimilation Project. I'm OSSLNR. The project is assimproj.org. The blog is, my blog at which I talk about a lot of technology is techthoughts.typepad.com. My company blog for the company I founded for this is assimilationsystems.com. So that completes my talk. Approximately on time, a little bit late.
So thank you, Alan.